prover was for a pure Lisp that Bob Boyer and I made up. So it just had cons, car, cutter, if, and equal, and then we wrote a theorem prover for that, focusing on induction. And later in the late 70s, we added it and made it more like Lisp, but it was still a homegrown Lisp. We were still writing our own compiler for it. And then in 81, MQThem came out, which was the next iteration, and also had a homegrown Lisp and a homegrown compiler. But people were using MQThem for pretty large models, and our compiler wasn't able to cope. And so in 89, Boyer and I threw away the old source code and started building a theorem prover around the applicative subset of common Lisp, so we wouldn't have to build a compiler. Boyer abandoned the project because he had other things to do in 91, and I carried on, and then Matt Kaufman joined me, and so the theorem prover that I will be showing you and showed you yesterday is really the product of Moore and Kaufman, but it's sort of thought of as another Boyer-Moore theorem prover because Boyer and I designed it and started it, but it's unrecognizable now from what it was in 1989. The progression of theorems started with really simple Lisp theorems. I'll show you one. And then some academic math in CS when we moved to UT and started having students like Shankar. And then the commercial applications. And I won't talk about these last two because I kind of talked about that last time. I'll talk a little about this. So here are some axioms. The constant t is different from nil. If x is nil, then if x, y, z is z. If x is not nil, if x, y, z is y. The car of the ordered pair constructed by cons x, y is x, and its cutter is y. Those are Lisp concepts, but think of that as head and tail and pair. Nil is the empty list, is the end of a list, and int-p of a cons is false. T and nil are, nil is overused. It's both the empty list and the false truth value. I just said that. Oh, except for this. We have a way of abbreviating constants, so quote 1, 2, 3 is really the list. It's this ordered pair constructed by that term, and you can think of it as that ordered pair. So a linear list is just a right-associated nest of pairs. So the very first theorem we proved in the 70s was the associativity of a pen, which is stated that way in Lisp. And the definition of append is recursive. If x is empty, return y, and otherwise construct a new list whose first element is the first element of x and whose remaining elements are those of appending the cutter of x to y. So I'm sure you know this, so I won't say it, but and then you're confronted with this theorem. And I'll kind of show you how the theorem prover goes about it. First of all, none of its ordinary simplification heuristics work, and it decides to try induction. It analyzes the recursion in the problem and decides it's going to induct on A. The base case is A is empty. And then it tries to simplify that by focusing on the recursive functions that are controlled by A. And this is one. Append A, B when A is empty is just B. This is another. Append A something when A is empty is just the something. Equal of two identical terms is true. And so we're done with the base case. Now the induction step is if A is not empty. And we get an induction hypothesis. And because we don't have quantifiers, the theorem prover has to posit the induction hypothesis before it starts. We just can't assume for all A less than for all lists less than the length of A, assume the theorem. We have to say which lists. And so we say, okay, we're gonna give ourselves the induction hypothesis for the cutter of A, and we're gonna try and prove this by reducing this to that. So now we have this as a hypothesis, we have that as a hypothesis, and we're trying to prove this. Again, focus on the things controlled by A. Append AB becomes cons of the first element of A onto the recursive call. Now this append can open up because it's controlled by something we know about, namely this cons. And so that becomes this. And then we focus on this append, and we know how to open it up, it becomes that. We have a rewrite rule that says two conses are equal if and only if the cars are equal and the cutters are equal. So that first part goes away, and we're left with this, which is the induction hypothesis. So we're done. So we've reduced the conclusion to the hypothesis, and we're done. So now let me shift over. Here's ACL2 again, a fresh version. Here's the definition of append I just showed you. It terminates because the size of X is getting smaller, and that's obvious because the cutter of a con is smaller. Here's that example. So we can run it. And here's the associativity of append, and I'll just let it spew out, and then just kind of briefly show you that it did an induction. It saw 3 inductions that it could do. 3 induction schemes are suggested. That append is suggesting induction on A. That append is suggesting induction on A. And that append is suggesting induction on B. Subsumption reduces that to 2 because these 2 inductions on A are doing exactly the same thing to A under the same conditions. So that's really, we have an induction on A idea and induction on B idea. But one is flawed. The B is flawed, and the reason is that this function, if we induct on B, our induction hypothesis is about cutter of B. But there's a B here that's not being changed as this function expands. And so we see no way that we can make this term in the induction conclusion become something like append A cutter B, which is what it will be in the hypothesis. So we abandon the idea of inducting on B and choose A. And it's not because of voting, it's not because we had 2 terms controlled by A, it's because of this flawed idea.
So you don't even try it. In a pre-processing stage, you scan through and you reject B for that.
Well, we analyze the recursive functions as they're defined, and we come up with some information like what variables they change, what variables they hold fixed, and that. And then we just apply that information to the theorem. We don't actually get through the proof.
Would it be different if you had a rewrite rule about append with a cons on the right hand
No,
side?
it should be, but it's not. That is to say, the theorem prover doesn't actually, since the induction selection is based on the definitions, it's insensitive to the current context of rewrite rules. And there are theorems where you really want to do an induction that is flawed because you know you have a rule around to take care of it. And at that point, you have to tell it, I want to induct on it.
So how much effort went into this analysis when you which decides what to do?
How much
Effort
on our part in coding it or CPU time used?
on your part.
Oh, I would say 80% of the heuristics were settled in 1975.
Oh.
And we haven't done much with induction since. Every now and then we find a little proof. Anyway, and then we get the cases I told you, and they simplified it true. Here's another illustration. This is a function that determines if the list X is shorter or equal to, in length, the list Y. So if X is empty, it's shorter or equal. If Y is empty, then X is not shorter than it because X is not empty, and otherwise you recur. This is an artificial function, but I want to show you, like for example, the first list is smaller than the second there, but not here. Okay, so that's less than or equal over list lengths. here's the theorem that it's transitive, okay? And it proved it, but I'm more interested in how it proved it. So let me go back and get there's the theorem. And here it says 3 inductions are suggested, but they merge into one. See, this is suggesting induct on A and B together. That's suggesting induct on B and C together. And that suggests inducting on A and C together. So let's just induct on all of them at the same time. So here you see, let me move that up. So this is a base case. A is empty. But technically we're just inducting on A. This is essentially another base case. A is empty. I'm sorry, A is not empty, but C is empty. And then in this case, we consider the possibility that neither A nor C is empty, and we assume the theorem for the cutter of each of them, and we prove it for that. And the whole idea is that all of the less than terms in this conclusion will step once to get back to that. And then we just deal with these by case analysis. So anyway, that's just part of the induction heuristics. And here's a function for inserting an element into an ordered list. So E is an element, X is a list that's implicitly ordered. If X is empty, just con Z onto the front. Otherwise, if E belongs before the car of X in a lexicographic ordering, that's a total ordering on all the objects in the logic. Then cons it on the front. Otherwise, take the front of X and insert E into the rest. And then, so for example, to insert Bob into that list, we put it after Alice and before Kathy. Now here's how you do insertion sort. It's obvious. If it's non-empty, you just insert the car into the result of sorting the cutter. So if we sort that list, we get Alice, Bob, Kathy. Now we want to prove that sort returns ordered output, and normally that would be stated with a for all. About for all I and j, if I is less than j, then a of I is less than a of j, or something like that. We have to define a recursive function. So we define ordered of x, that either x is empty, or x has one element, or the first thing of x is less than or equal to the second, and the rest is ordered. That's our notion of order. And then we can try to prove this, that insertion sort produces ordered output. And it proved it. And again, I'm not going to look at anything but the induction for a moment. Well, no, I will. Yes, let me back up. Here's the theorem. We started by an induction on X. We did some stuff. I'll tell you more what later. But notice this is a really interesting subgoal. It's a generalization of what we were trying to prove is that thing up there. We had simplified our goal to this. And then we generalized it, replacing the call of sort by a new variable, it, which happens to be just the first and last letters of that function. Anyway, and now we're trying to prove that if it is ordered, then inserting x1 into it is ordered. And that's the really crucial property of insertion. And we didn't have to tell it. It discovered it in the course of the proof. So it gave that a new name. It finished the base case of the induction it was in. And then it came back and did an induction to do that, which it succeeds at. And that was that. So this fact that it can generalize and do more inductions is really important because trivial theorems, simple theorems, are often proved without a lot of user effort, which makes a big proof easier, because you have in mind a complicated argument that you're going to have to basically tell the theorem prover, but it's based on lots of little facts, and those little facts you just state. and it typically proves them, and then you glue them together if it doesn't see how. So here's a new function called remarkably fast sort, which ignores its argument and returns Alice, Bob, Kathy. Okay? And so if I remarkably fast sort Kathy, Alice, Bob, I get a correct answer. So I'm like, if somebody had paid me to write a sort algorithm that satisfied the spec I've given so far, this would be a winner. And I can prove that the remarkably fast sort produces ordered output. Okay? But unfortunately, of course, the remarkably fast sort of Jim and Susan returns Alice, Bob, Kathy, which is not what we meant by sort. So, as we know, we have to say more about what it is to be a correct sort, and that involves the notion of permutation. So I reach out into the library and I grab a book on permutation. And so, for example, Kathy, Alice, Bob is a permutation of Alice, Bob, Kathy. But these two lists aren't permutations because there's two Kathys into one and there's only one in the other. So then, here's the definition of perm. Again, it's a recursive function. X and Y are permutations. If X is a cons, then its first element has to be in Y, and the rest of X has to be a permutation of the result of removing that element, one occurrence of that element from Y. So now I can try and prove that perm that isort returns a permutation of X. And I did it, so that's good, I know that. And if I tried to prove that remarkably fast sort returns a permutation, it fails. Trying to prove that Alice is in the list I'm sorting. So that's the end of that demo.
Could you somehow from the failure say that it's unprovable, or do you have to?
No, we don't try to generate a counterexample of the formulas we failed to prove, partly because it's too hard, and partly, but I'll come back to that, but partly also because we've generalized the formula along the way, so a counterexample there won't necessarily tell you your original. But obviously, if you could construct a counterexample there and then back it up through the generalizations, you might have a counterexample above. And people, in fact, Pete Manolios at Northeastern University in Boston has a version of ACL2 for teaching that does produce counterexamples. So here's a kind of sketch of how the theorem prover works. The user puts a formula into this pool. It's always drawn out by the simplifier, which does everything it can to it, and either puts new formulas back in to prove instead of that one, or if simplification can't do anything, it gives it to another routine which tries to eliminate certain function symbols. And it either puts something in the pool or gives it to something that uses equalities heuristically. And if that doesn't work, we try to generalize, and if that doesn't work, we throw away anything that we think is irrelevant, and then we go to induction. And the whole idea is you mainly work on simplification, and the rest of this is trying to prepare a formula for induction by making it as strong as it might be.
So the rewriting.
Yeah, go ahead. Yes, and simplification is where we have spent like 40 years. It's got evaluation and propositional calculus decision procedures, use of equality, linear arithmetic, some heuristic nonlinear arithmetic procedures, rewrite rules, recursive functions, congruence relations, all kinds of stuff is piled in there. It's a very complicated and sophisticated routine. And almost, I would say 95% of CPU time is spent in that one circle.
What is a meta function?
A meta function is another theorem prover that you proved correct. And when you proved it correct, you can incorporate it into the simplifier. So anytime a formula with certain terms in it arises, you apply this. And you know that it preserves the meaning because you prove that eval of the simplifier is equal to the eval of the original.
That's like, that's a reflection.
Yes, it's a reflection. And then so here we have the user sitting at the theorem prover, but it's backed up by this library of books. When the user poses a lemma to the theorem prover, if the theorem prover proves it, it gets into the library or the database, and subsequently, for the next theorem, that lemma is available. So in a certain sense, the user is programming the theorem prover by understanding the effect on the prover of the lemmas in the database. And if you have if you want to prove P implies Q, you might prove P implies R and R implies Q, and get both of those rules in the database and then expect the theorem prover to just change them. So let's use lemmas. I'm going to shut off some output so we don't see some. So let's prove that append AB is a permutation of append BA. And we give that to ACL2 and it fails. And I'm going to show you, that's what I asked it to prove. I shut off output so it doesn't show me the intermediate formulas. But I just wanted you to see that it tried lots of things. It actually tried several inductions and it eventually gave up. And it identified what we call some key checkpoints. And the typical user just looks at that last screen. And in fact, just the first thing you always do is you look at those formulas and you say, are they true? And if so, why? And my eye is immediately drawn to that member, carve A, append BA. And I know, well, gosh, something's a member of the append of two things if it's a member of one or it's a member of the other. So I don't even want to be looking at that term. I just want to get rid of it. And so I proved this lemma, that member E, append AB is the OR of member EA and member EB, which it proves by induction without any trouble. And then I say, okay, let's try perm again. And this time it worked. And that's that's what we call the method. And the method is in quotes because it's really not a method at all. It takes a lot of intelligence to identify the subterms you want to focus on and simplify, and the rules that you can prove that won't screw you up later. But it's called the method, and it works surprisingly well. So here's another theorem. Let's prove that if you sort something and then sort that, you get the same thing as the first sort. Again, it fails. And now here, I look at applying the method, I see, oh, I need to prove that I sort commutes with insert, okay? Okay, that's nice. I could go off and try and prove that.
Why didn't it generalize that?
It probably did and failed, and it shows you something that is doesn't have the generalization. Yeah. So a lot happened. See all these formulas that got generated. So it tried a lot before it gave up. But in any case, but now here's the formula I'm trying to prove. And thinking less like a robot and more like just a normal person, I think, well, gee, this output is ordered. And if I could prove that isort of an ordered list is the identity function, then I would be done. So instead of following the method, I actually do something, quote, creative. And the creative act is to posit that theorem, that if X is ordered, then equal isort X, X. And it proves that. And then I say, well, now prove idempotency again. And it proves that without induction. It just says, just put together the two facts that he's shown me, and I'm done. And so that's a more typical way to behave on interesting theorems, is that you have a proof in mind. And it involves some limits, and you prove the limits and then expect it to Now, another fact about ACL2 is it supports congruence relations. Perm is actually an equivalence relation. When I introduced perm with that book, I proved the theorem perm is an equivalence, I think it's called. Yeah. So perm is an equivalence, it's a Boolean relation, it's reflexive, symmetric, and transit. So now ACL2 knows that perm is an equivalence relation. And that theorem says that perm is a congruence in the second argument of member. And so what that really tells the rewriter is that if you ever see a member expression and you're trying to preserve equality in a rewrite, you can replace the second argument by any permutation of it. So perm AB implies the equality. So in general, the form of these lemmas is that's an equivalence relation, that's another equivalence, or it's the same equivalence relation. That's a function that's the same as this except for one position, which has been replaced by these two things that are known to be equivalent. And so this isn't stored as a rewrite rule. This is stored in a table that says when you're rewriting member to preserve equality, you can use any perm relation as a rewrite rule. And so let's prove that. Okay, we proved that. It did a couple of inductions, but okay, I don't care. And now I'm going to attack a non-theorem just to show you. See, here we have a member and an I sort of A, but I have the rewrite rule. You didn't think of it as a rewrite rule, but I have the rewrite rule perm I sort, which we proved earlier. And if you think of this as an equivalence relation, it says I sort of X is equal to X when you're trying to preserve permutations. And the congruence rule tells me it's sufficient to preserve permutations in the second argument of member, and that I sort's in the second argument of member. So when I give the theorem prover that formula, sorry, I want to put that on the top. Never mind what it did. Notice that it rewrote the goal by getting rid of the I sort. It rewrote with a rewrite rule called perm I sort. It's the rule we proved, but used as a rewrite rule even though it's a perm. So that's and we define a lot of equivalence relations and a lot of congruences because we have such a concrete universe of just, unlike, for example, we don't have sets. And if you don't have sets, then how do you represent sets with lists? Well, you can use ordered lists, you can use list without duplicates, you can just use list with duplicates. And then you can define a set equality that quotients all that down to sets, lists that represent the same finite set. You can't do infinite sets because it's just a nice inductive list. But anyway, so we use a lot of equivalence relations, and some are very sophisticated, like the x86 state is equivalent. Two x86 states are equivalent provided the only things that's different in them are parts of the stack that you can't see. Anyway.
Jed, I have two quick questions for you. So when you say something like induction on mem_b,
Yeah.
that's interesting. It's not induction on a variable, but it's induction.
No, that's the name of a rule. When member was, every rule in the, think of the system as a big collection of rules.
Yeah.
And the most common rules are rewrite rules. Replace this by this conditionally under these hypotheses. But we have other rules like congruence rules that tell us something's a congruence or an equivalence rule. And the induction rule tells us this function symbol suggests the following induction, and it's connected to an induction scheme.
Okay, so it's induction scheme.
So this is just telling us what rules got used. And when you get down into the nitty-gritty of trying to drive a big proof, you may find that rules that you've already proved get in your way. They transform the theorem in a way you don't like, and you have to, what we call disable them. You slip into a theory where that rule isn't available by disabling it. And I haven't shown you, but you can give hints and all kinds of stuff to control the context in which the theorem provers operate.
So one other question on failure, when you show these checkpoints, can you you say a word or two about what the checkpoints are? Are they the first failure points or the most promising?
Yeah, the maximally simplified before generalization, but we go ahead and, what really happened is when we have maximally simplified it and we haven't done anything that would generalize it yet, we proceed on with the heuristics to try to prove it, because generalization and induction might work out. But if it doesn't, we report that checkpoint as the thing.
So these are like the earliest backtracking points.
Yeah, right.
I have a
Yes.
small question. So do you introduce new terms through the equivalence? Might you say, I'm trying to prove member or something in A, let me try if there's something to do with insert of A?
I'm sorry, I don't
I mean,
understand.
do you, you say, okay, now if I'm proving member EA, I can look for something that's a permutation of.
Yeah, I
A.
can look for
And
rewrite
then,
rules about
I try to see if there's, if member E insert of A.
Uh-huh.
And I'm worried that, you keep going insert of.
Right. Oh, I see. Could I, yes. You're asking basically, never mind our use of congruences. Our rewrite package has, I mean, if I write the rewrite rule, f of A is equal to f of A, if I prove that as a theorem and pose it the way I just said, it would infinitely rewrite. If I switch it so that it says f of A is equal to f of A, then mathematically they mean the same thing, but operationally it means replace two f's by one.
But here it seems to replace the insert of A by A. So it
Yes.
seems to have some kind of simplification.
Well, that's because the rewrite rule that it was using is one of those nice equivalences that says this is equal to that. If I had posed this rewrite rule the other way around, it would want to rewrite the variable, which it doesn't do. Okay? And we do have heuristics to break loops in rewriting, but they don't catch every possibility. Okay, so back here. So you saw me use a book on Perm. On GitHub, we have the community's collection of books, and it's over almost 6,000 books now, with a whole bunch of definitions and a whole bunch of theorems. And every time we change, Matt and I change the theorem prover, we rerun this regression on cluster. Takes a couple of hours, and it's a great way to find heuristic errors. It's easy to change the heuristic theorem prover so that it can prove a theorem that it failed on, and without you knowing it, it can no longer prove theorems it used to. So it's great to have a big regression suite.
How do you curate the library? Can anybody contribute? Do you have an
Anybody
process?
contribute, but they have to make sure the book will certify under the current system. And then Matt and I, if we change the system, when we change the system, we run the regression and we're obliged to fix it if we break somebody's proof. And that's the way we find heuristic fixes. It's tedious. It's very tedious. So that's kind of brought us to the 80s, sort of, but congruence just didn't exist in the 80s for us. But anyway, in the 80s, we went to UT, and so, for example, we proved the undecidability of the halting problem and the invertibility of RSA, and a graduate student, Rusinoff, proved Gauss's law of quadratic reciprocity, and it took him 348 lemmas. And Shankar here proved Gödel's incompleteness theorem, and it took him, 1,700 lemmas. So we were building up a library there, but we were really also focused on computational problems, and we built in the 1980s a verified stack that started with a gate-level description of a microprocessor that implemented a machine code, an assembler linker and loader that implemented a stack-based assembly language like the JVM, a couple of compilers.
Python.
Yeah, Python. A couple of compilers, an operating system, and some applications. And all of those theorems fit together so that if you took an application and verified it with respect to the semantics of the programming language here, and then you compiled it and assembled it and linked it and loaded it and ran it on the microprocessor, it would behave as predicted by that. So this was a complete, well glued together stack, and it was called the computational logic stack. Computational logic being the name of a company we had. And the chip was fabricated in '92. Anyway, and then in '95 we started the Intel business, and the rest I told you yesterday. Now I want to go back to a demo about, because I talked about the importance of speed, and I wanted to show you a little bit how you get more speed out of the system. I'm going to define fib1 to be the Fibonacci function. And this declare is the way Lisp lets you declare type information, and we added a new declaration called xargs, which lets us then add a whole bunch of things. And so I've written a declaration that says this function expects its argument to be a natural. But I've also told it, don't bother to verify that. So you can think of this as of no use whatsoever right now. It's just there for my convenience. And I have the Fibonacci function. So I'll define it. And now I'll write, you know, fib of 1, fib of 2, fib of 3, 4, 5. You get the idea. It's fib. But of course, it's an exponential computation because of the way fib was defined. So, for example, if I do fib of 10 and time it, well, I can't measure it in hundredths of a second. And fib of 20, I still can't measure. But fib of 30 started to take about a quarter of a second. And fib of 40, well, that's going to take a while. And so the first step, when you see a computation taking a long time, the first step is to verify the guards. Because what's happening right now is that the theorem prover is checking that the guards of fib, that every time you apply plus, every time you apply minus, every time you do anything with arithmetic, you're dealing with a number. And so there are a lot of runtime checks happening in that in all of these computations, but this computation is so big it took a long time, 28 seconds. But now I can say, verify the guards of fib1. And so it generated the formulas, and the only interesting one is this one. It says if n is the natural, that's what we assume, and it's not 0 and it's not 1, then n minus 2 is a natural. We had a theorem like that for n minus 1, but that was just spotted by a preprocessor and dismissed. This one we had to actually prove with arithmetic. Anyway, it proves it's easy. But now we know that if we call fib1 on a natural, then every arithmetic operation we encounter will be facing numbers, naturals in fact. And so that allows it to run a lot faster. So this computation took 28 seconds a moment ago, and now it takes a second. Okay, so I sped it up by about 30 by proving away those runtime checks. Now, of course, there are other ways to define fib. I could define fib in the linear sense, where fib of n is just keeping in j and k the last two values it returns and adds them together and shifts and changes those variables. So here's the linear version of fib. And so now I can compute fib of 40 in almost no time. But of course, the question is it fib? And so here's the theorem that relates fib2 and fib1. I won't say more. It's just the general relationship that explains what j and k are doing in terms of fib. And so it proved that, and I don't know if it needed more than one. No, it only did one induction, so that's nice. But now I can define, and this is kind of an ugly trick, but I'm trying to show you how we do things sometimes. Now I can define the function fib of n, and MBE means must be equal, and I can provide a logic definition and an executable definition. And the problem is they have to be equal. So the theorem prover will accept this if it can prove that fib1 of n is equal to fib2 of n 0 and 1. And if it proves that, then from the logical perspective, the definition of fib is fib1. But whenever I'm called to execute it, I actually run the code of fib2.
Did you show us the execution of fib2?
Pardon?
Did you show us the execution of fib2?
Yes, I did.
Okay.
Yeah,
How long did it take?
Not measurable.
not measurable. Here's the execution of fib2, and it didn't take any time. Anyway, so, okay, I just did that. Now I have this function fib, and I say, well, what's fib of 5,000? Which if I were running the recursive fib would take forever, but here computes an answer really quickly, and yet I can prove theorems about fib using the other definition. So that's nice. And then finally I want to show you one more thing. Remember fib1, that was the version with the guards verified, and it still takes a second to run on 40. Because ACL2 is a functional language, we can memoize it. So there is a facility in ACL2 that you can say memoize and you give it the name of a function. And it backs up that function with a memo table. And now, for example, I can say, what's fib1 of 5,000, which would have taken a very long time. But now what you're going to see is a run of that function in which every result that's been seen before is stored and regurgitated. And so it took 0.01 seconds to do that big computation. So the user has a variety of ways to speed things up. But the most common one is to define things in an efficient way, and maybe sometimes to define an elegant way that you want to reason about it and prove them equivalent. Now, in the last few minutes, I want to talk a little about metafunctions and the whole idea that because ACL2 is a nice programming language for writing theorem provers, you can write provers in it and prove them correct. And that's used a lot. And so, for example, a common use is when you're symbolically executing machine code against an interpreter like the x86, you want to normalize address expressions. And you want to be able to answer questions like, is this address possibly equal to that address? Because you want to apply what we call a read over write theorem, where you've written to one address, you're reading from another, and you want to know they're different so that you can ignore the right. And so we have verified metafunctions for doing things like computing bounds on arithmetic expressions, doing interval arithmetic, and that's all been verified. And we have verified decision procedures like the BDD package. Another common thing is to transform a formula into a different domain, and the most common use of that is to do bounded arithmetic by turning it into a Boolean propositional problem and bit blasting with something like a BDD package or a SAT solver. And also checking proofs delivered by other tools. And so let me show you one verified tool. This tool was written by Centaur, it's called GL. Takes a while to load because it's a big verified system. And so now I'm going to define a couple of weird functions that hardware designers might know about. This is a multiplier that mods it out at 32 bits. Okay, so you multiply x times y and then AND it with a mask of 32 ones. And this is the function that counts the number of ones in a 32-bit word in a very mysterious way. Those of you who know machine code will have seen this function before, but I mean, just look at it. it takes the bit vector v that you're counting, shifts it down by 1 and masks it with that hexadecimal number. And then subtracts that from v, and then it masks that with that other, that numbered hex 3s. And so on. I mean, it makes no sense. You gotta admire the guy who thought of it. But there it is, that's a function. And now, in the logic, in Lisp, there's a function for counting the number of bits in a word, and here it is, this is its definition. And so for example, if x is even, its log count is the log count of quotienting it by 2. And if x is odd, then you add 1 to that same call. So so that counts the number of bits by just looking at counting, shifting it down and looking at the ones that you encounter. And so, for example, the log count of this binary number should be 3 because there's 3 ones in that. And the fast log count of that binary is also 3, magically by that bit twiddling that we saw. What you'd like to do is prove them equivalent. And one way to trying to do that algebraically is really a mess. Proving it with a bit blasting is not hard at all. So this is the interface to the tool that was verified when I loaded that book. And it says if x is an unsigned byte of 32 bits, then the fast log count of x is equal to the log count of x. And then this is a hint for how to enumerate the bits in x for prepositional encoding. But that proved it. Now, you can't see much, but what happened was it converted all the arithmetic in that into 32-bit circuit descriptions, ands, ors, nots, and so on, for plus and times and minus. And then applied, in this case, a verified BDD package. And that's a very typical thing that a hardware designer will do in ACL2 is he's looking at some code, he knows what it's supposed to do, he proves it with bit blasting, and then glues this theorem, which is a full-fledged, actually it's a theorem. If I say, pretty print, what's the name of the theorem? This. It is actually this theorem, and it exists as a theorem, and the fact that it's a theorem was proved when we proved the correctness of the bit blaster and the correctness of the BDD package. And so that theorem can now be used as though it were proved, by induction or however we proved it, and can be used to glue together other theorems. So that's a very typical tool that's in the distributed books. Finally, another use of ACL2 is to verify tools that are used to check other provers. And a recent example will be talked about next week by Marine Huell, who is a SAT researcher at UT actually. And he used a SAT solver to prove the Boolean Pythagorean theorem, which says that every red-blue coloring of the positive integers contains a monochromatic solution of the Pythagorean formula. And he finitized it and solved it with a SAT checker, but the proof is big. And he'll talk about that later. What do I mean by the proof is big? To produce the proof took 13,000 hours of CPU time. The proof is almost 200 terabytes, okay, so that constitutes a big proof. It took him 22,000 hours to optimize the proof, which is actually, it's a slightly bigger proof that's easier to check. And the optimized proof is 194 terabytes. And all of that was done on a cluster of 1,200 CPUs and took 34 hours of wall clock. Now, unfortunately, SAT checkers have a history of claiming incorrect results. And so the SAT community has accepted that if their satisfiability checkers claim that something is not satisfiable, of course, if they claim it's satisfiable, it's easy to demonstrate. You just show a satisfying assignment. But if it's not satisfiable, it's not easy to demonstrate. And so the SAT community has agreed that these proofs should be checked by a verified checker. And so Matt Kaufman and Marine wrote a checker in ACL2 called refutation P, and Matt then proved the theorem that a formula is a formula, propositional formula in the right format, and proof is an alleged proof of it that is checked successfully by refutation P, then there is no satisfying assignment to formula. So that proves the correctness of the refutation checker. It took about 8 pages to write it down, and that was verified by Matt with ACL2. And then, so the ACL2 checker takes 8,000 hours to run on that 200 terabyte proof and checks it. Now, it turns out that the ACL2 checker runs at about half the speed of the fastest unverified checker. So that's the bad news. It happens to run about 10 times faster than a verified checker verified with Coq, so that's the good news from our perspective. And our SAT checker is to be used in SAT competitions to avoid this problem. But the main idea is that trustworthy checking of huge proofs is feasible. I mean, here we have a checker that is practical to run, has been verified by a mechanical tool, and runs fast enough to actually handle these big proofs.
One question about that.
Yeah.
So clearly it was parallelized somehow, right, when he was actually checking it?
Pardon?
The checking was parallelized?
Yes,
So
yes, it was parallel.
Was that the parallel version done in ACL2, or was that done outside?
No, what was happening is Marine set it up so that he could run different parts of the problem simultaneously on his cluster, using the ACL2 checker for each, I don't know, there's probably a million
Each piece.
parts. And then using the checker to check the gluing together of those pieces.
And what about the reduction of the Boolean Pythagorean triples problem to SAT? Does that
That's
verify that?
no, that's Marine's problem. Yeah, right, but it's a good.
In Coq, they did even that. Or at least
Well, we did something, I mean, I don't actually know exactly what Matt verified there, but I know that it's fairly subtle because he actually, his refutation checker works on a file. And it takes a file and parses it out and confirms that it states a certain formula. But he doesn't verify the parser. He uses the parser and then checks the output of the parser as the formula that you were supposed to verify. But
No, I
whether
mean-
or not he checked the encoding
Yeah.
of the problem, I can't say. But Marine will be talking next week, I think. So you can
Because
ask.
you could have maybe composed the bit blasting with the SAT.
Yeah, maybe, I don't know. So the take-home message is that this theorem prover is used in industry. We need people to formalize the specs and steer the prover, but you don't steer it with the level of proof checking commands typically. You can. For any goal that ACL2 prints out, you can attach to your theorem a hint that says when you get to goal 1.3.7, then disable this rule and use this fact, or do induction on that, or whatever. So there's a proof checking facility, but it's rarely used because of this proof maintenance problem, wanting to redo proofs every time a design changes. So you don't want a human in the loop in the end. But the user has to be mathematically precise and creative. but the machine takes responsibility for the correctness of proofs. And I find it both challenging and liberating because, I mean, when I'm programming the theorem prover, I'm paranoid because I'm afraid I'll make a mistake. But when I'm using the theorem prover, I feel so free because I can just guess any old thing, and I may be wasting my time, but I'm not making a logical error. And anyway, it's great fun. I love it. Okay, that's the end. Any other questions? I'll be around for a while.
So let me repeat Vladimir's question from before the lunch break. So he posed the challenge of how to explain automated proofs to mathematicians. So what's your opinion on this, or your view on this? How to convince a mathematician that an automated proof is actually valid?
Well, I mean, first of all, I'm more interested in explaining an automatic proof to a hardware designer or a programmer. And they don't actually, it's not even an option to show them a formal proof because that's not what they're interested in. And the proofs are so large, they would die before they finish reading. So the best answer I can give is standard ones. Either the prover has been verified by some mathematical means, or it's been verified by the social process of being in the public domain, and many people look at it, which is what our theorem prover relies on. And the third possibility is that for any particular proof, at least in our system, the proofs are generally follow from lemmas that in some sense are intuitive. I mean, the idempotency of isort followed from the fact that isort is an identity on ordered lists and then it produces an ordered list. And I should hope that I could say those two things and the guy would know that it's that's an argument that's idempotent. Now, for a proof of the size that we're talking about there, I don't have a clue what to do except to trust the machine.
So has the first thing been tried for ACL2 to prove it correct in itself?
No, not for the code that you've seen. A graduate student named Jared Davis built a version of ACL2 with a simplifier and an induction package and a quality use and verified it. But the whole thing hasn't been verified. And the way he verified his prover was to write a proof checker and then to use the proof checker to verify a tautology checker and then use the tautology checker to verify something that's a little better than that and to build up. So he built a stack of 11 provers, each of which was proved correct by the bottom one, and the bottom one was a proof checker for first order logic. And so he has a convincing, runnable, it runs pretty fast. And by the way, it's been run on the system, Magnus, who's?
Magnus
Magnus.
Yeah, Magnus's system that compiles, together, Jared and Magnus wrote a compiler for Lisp that's known to be correct by Magnus's system, and so Jared's system will run on that. So, but that's the extent of the effort to verify the prover. And at the moment, our prover is subject to human error by me and Matt, but only by me and Matt. No one else touches the code, although users often make suggestions, but we are responsible for every change. And the justification of that is that for 40 years, I've basically been unsatisfied with the prover and not ready to say, okay, it's right. Now I'm going to prove it correct because I will change it tomorrow and I don't want to prove it correct again. And so you know.
So I think Jared's work is
Pardon?
very impressive. Jared's work
Yes,
is-
Jared's work is very impressive. It's called Malawa, this group. So if you Google Malawa, you'll see this.
So how many proofs could he verify from the ACL2 books? Like, is it?
Oh, he hasn't tried the whole thing, but hundreds.
Oh.
Yeah,
So
it's a good proofer.
Well, what's the reason it would be failing on some?
Oh,
some
he
books?
didn't implement a linear arithmetic decision
Oh.
procedure. But, we know how to do that. Okay? All right,
So,
thanks.
yeah.